Blue civilization. That is the name humanity gave to what it built on and inside the ocean when the alternatives began to run out. And before this episode ends, you will see its most extraordinary expression, a city of light on the floor of the sea, in total darkness, half a kilometer below the surface, with the weight of 50 atmospheres pressing on every wall. And to understand how humanity builds its way to that moment, you have to start with the question it was built to answer. Right now, 300 million people, roughly the entire population of the United States, live on land that will fall below annual coastal flood level by 2050. Not worst-case scenario flooding, annual flooding, every year, on schedule. Within the lifetime of children already born, the ground beneath those 300 million people will be underwater before the calendar turns. But here is the fact the sea level reports almost never lead with. In most of the world's great coastal cities, the water is not just rising to meet the land is sinking to meet the water, faster, much faster. And the response humanity has built, first cautiously, then ambitiously, then with an audacity that has no precedent, is not a higher seawall. It is a new kind of city, built on the water, and eventually, inside it. This is that story, from first floating neighborhood to the cities of the deep. In 2050, Jakarta, a city of more than 30 million people on the north coast of Java, will be partially submerged, not by a storm surge, not by an extreme weather event, by ordinary physics acting continuously on decades of human engineering decisions. The mechanism is groundwater. Jakarta sits on soft deltaic sediments, the accumulated material of river systems meeting the sea over millions of years. For most of its modern history, the city extracted water from underground aquifers. When groundwater is withdrawn from below soft sediment, the sediment compacts under the weight of everything built on top. The ground sinks, flooding increases, more wells are drilled, more compaction, more sinking. The feedback loop is self-reinforcing and slow enough that no single decision was ever clearly the wrong one. The numbers are arresting. In Jakarta's northern districts, the oldest, most densely occupied, most historically significant parts of the city, subsidence rates of 20 to 28 centimeters per year have been recorded. The global rate of sea level rise is 3 to 4 millimeters per year. Jakarta is sinking in some places roughly 70 times faster than the ocean is rising. By 2050, subsidence alone, independent of climate change, will account for between 85 and 88% of the city's relative sea level change. The ocean is not coming for Jakarta. Jakarta is sinking into it. This mechanism appears in city after city wherever soft coastal sediments and groundwater extraction combine. Bangkok sinks measurably. Ho Chi Minh City sinks. New Orleans has been sinking for generations. Manila sinks. Houston sinks. The cities most threatened by coastal flooding are concentrated precisely in the river deltas and coastal lowlands where civilizations first settled because the soil was rich and the water was near. The traditional engineering response, the seawall, works within a range. Below a certain height and exposure threshold, hard coastal defenses are expensive but manageable. Above it, costs do not scale linearly, they scale exponentially. A seawall calibrated for a 1 in 100 year event built on compacting ground in a tropical storm zone in a megacity with decades of displaced utilities beneath it, that is a different financial universe entirely. For some coastal cities, the arithmetic of hard defense already fails. Adaptation economists call it the retreat threshold, the point at which maintaining and rebuilding defenses costs more than relocating or fundamentally redesigning. That threshold is not theoretical. It appears in mainstream policy literature. It is already here for some communities. The ancient world already understood the alternative. The Uros people of Lake Titicaca have built floating islands from totora reeds for centuries, more than 2,000 people across 90 islands, each one continuously maintained as older reed rots beneath. The Tofinu people of what is now Benin built Gonvier on Lake Nokwe to hide from slave raiders, a complete civilization constructed on water as a deliberate act of survival. Makoko, the vast informal settlement in Lagos Lagoon, houses an estimated 250,000 people in timber pile structures above the water. Canoe-based circulation, complex social and commercial networks built entirely on and above the surface. The evidence is ancient. Large populations can sustain long social lives on water. What has never been attempted is modern urban density with modern infrastructure: water, power, food, sewage, emergency response, data, governance, education, healthcare, running continuously on a platform that floats. That is the project, and the first serious attempt at it is already in the water. A floating neighborhood in a Korean harbor is the beginning of an answer to the greatest coastal emergency in human history. But it is only the beginning. What that neighborhood actually looks like, how it works, and what makes it extraordinary is something no rendering has ever fully shown. Step off the ferry at dawn, and the first thing you notice is the light. It comes from below, beneath the translucent walkways connecting the hexagonal neighborhood clusters of the Reef District, the expanded concept built from the original Oceanics Busan prototype. The water glows with a pale bioluminescent shimmer. Organisms have colonized the submerged mineral surfaces of the foundation. The city has been in the water long enough that the ocean has claimed its underside as habitat. It is not a platform floating on water. It is something growing from it. This is the design intention. The architecture of a floating city is the architecture of interconnection. Each hexagonal module is roughly 60 meters across, about the width of a city block, linked by retractable bridge walkways that allow slight differential movement between platforms in wave conditions, while maintaining pedestrian continuity. The interfaces, where modules look onto the central lagoon formed by clustering, are lined with restaurants, markets, and community spaces opening directly to the water. The outer faces are residential and institutional, with high parapets to deflect spray. The hexagonal form is not aesthetic. It is the most efficient tessellation geometry for a growth system that needs to expand in multiple directions without creating wasted edges. A hexagonal module connects to up to 6 neighbors, each connection point simultaneously a structural joint, a utility interface, and a pedestrian corridor. The geometry distributes load evenly around the perimeter. And critically, hexagonal growth means a floating city can add one neighborhood at a time without taking the entire system offline, restructured, or refinanced. This is the strongest argument for modularity over a monolithic floating slab. A single large platform converts the entire city into one failure domain. Modularity contains damage. Modularity is a resilience architecture. The mooring system holds the platform in place without rigidity. Tension leg moorings fixed to the seabed allow the platform to rise and fall up to 2 meters with daily tidal range, while Tension leg moorings fixed to the seabed allow the platform to rise and fall up to 2 meters with daily tidal range while maintaining horizontal position to within a few meters. On deck, the motion is imperceptible in ordinary conditions, not a ship, a neighborhood that happens to float. But the hull below the waterline, that is where the design becomes something else. To understand what makes the Reef District's hull extraordinary, you first have to understand what makes all marine concrete ordinary. Steel rebar in a marine environment is attacked continuously by chloride ions that penetrate the concrete matrix, initiate corrosion, expand, and eventually crack the concrete from the inside. The entire long-term maintenance burden of conventional marine structures is in large part a rebar corrosion problem. It creates maintenance cycles that never end and costs that never stop growing. The Reef District solved this at the design stage through fiber-reinforced polymer reinforcement, composite rebar that does not corrode. The chloride pathway is simply absent. But the designers went further. Instead of treating the hull surface as something to be defended from the ocean, they designed it as something to be activated by it. Low-voltage direct current applied to the hull's outer surfaces triggers mineral accretion. Seawater's dissolved calcium carbonate and magnesium hydroxide precipitate onto the energized surface, building a continuous mineral coating. It grows the way coral grows because chemically it is growing by the same mechanism. Coral polyps and other sessile marine organisms colonize the accreting surface preferentially. Within 5 years of launch, the hull is alive. Within 20, it is an artificial reef with biodiversity density exceeding most natural reefs in the surrounding region. The Reef District is not protected by the ocean by its hull. The hull has become part of the ocean. Energy is distributed and layered. Solar canopies over the main public spaces, tidal current turbines at the mooring anchors, waste heat recovery from the desalination system feeding climate control for the covered market halls. Fresh water comes from reverse osmosis desalination, the best current systems operating at 1.7 to 1.8 kilowatt-hours per cubic meter, manageable within a distributed marine power budget. A community of 12,000 needs roughly 1,200 to 2,400 cubic meters per day, a continuous desalination load of under half a megawatt. Food is the honest reckoning. The rooftop greenhouse decks grow leafy greens, herbs, and tomatoes, crops where controlled environment agriculture genuinely excels, with lettuce yields of 60 to 105 kilograms per square meter per year achievable under optimized conditions. The outer perimeter nets carry shellfish and seaweed, which filter the surrounding water and produce protein with near zero energy input. Seaweed culture alone, ulva, kelp, Gracilaria, can yield tens to over 100 tons of dry weight per hectare per year. Together, the Reef District produces roughly 30% of its vegetable requirements on platform. But calorie-dense staples, wheat, rice, corn, remain imported. NASA's Controlled Environment Wheat research shows why. Feeding 12,000 on locally produced wheat requires roughly 12 to 30 hectares of growing area and a continuous electrical input measured in tens of megawatts just for artificial lighting. That is an energy commitment that overwhelms a floating platform's power budget entirely. The honest engineering position, grow what the thermodynamics allow efficiently, import what they don't. A 30% local vegetable supply from a platform that has been in the water for a decade is a genuine achievement, not a failure. Walking through the central market at midday, the smell is salt air and grilling fish and the loamy warmth of living soil, entirely unexpected above open ocean. Children play at the fountain in the hexagonal public square. The fountain runs on desalinated seawater, recirculated in a closed loop. The deck motion under normal conditions is under 3 centimeters. The first floating city is remarkably, stubbornly ordinary. The question is whether it can scale, and whether at scale the city can become something genuinely new. The Reef District is a neighborhood. What happens when the scale becomes a city, when the geometry expands to ring a whole lagoon, when the city is built not by a harbor but by the open sea as a national survival strategy? The Maldives is a nation that sits on average approximately 1 meter above sea level, not 1 meter above flood tide, 1 meter above mean sea level. The climate projections for this century do not inconvenience the Maldives, they threaten to delete it from the map. The Ring Atoll is not an architectural experiment, it is a national survival strategy, and it looks the part. Set several kilometers from Male, the capital, the Ring Atoll uses a lagoon-centric ring form, a broad circular arrangement of floating modules around a protected central lagoon, smaller residential structures filling the interior, larger commercial and civic towers rising at the outer edge. From altitude, it resembles the natural coral ring formations that built the Maldivian islands over millennia. That is explicitly its design reference. The city is shaped like the islands it will eventually stand in place of. The Ring Atoll introduced an engineering principle that would define floating urban design for the following decade: the amphibious module. The Reef District assumes fixed freeboard. The distance from waterline to deck stays constant. The Ring Atoll uses variable ballast chambers, allowing each module to adjust its vertical position by up to 2 meters. In storm conditions, the deck rises. In calm, it lowers until residents step almost directly from their platforms onto the water's surface. This is storm management architecture, not comfort design. When a severe cyclone approaches, the entire city rises. The mooring system, derived from deep-water oil platform engineering, maintains horizontal position through the full vertical excursion. A city that can literally lift itself above the worst a storm can offer and then settle gently back down when it passes. The central lagoon is, by design, extraordinary. Every module's waste stream is processed through closed biological treatment before anything enters the interior water. The lagoon is cleaner than the open ocean surrounding it. Lagoon visibility exceeds 30 meters. Parrotfish and surgeonfish have colonized the city's underside as permanent reef habitat. The boundary between the city's infrastructure and the ocean's ecology within 1 generation of occupancy has dissolved. The Blue Commons extends this model to 100,000 people, and in doing so confronts a supply problem that no surface renewable can solve alone. Baseload power, available at night, in calm air, in cloud cover, year-round. The Blue Commons runs on the ocean's own thermodynamics. Ocean Thermal Energy Conversion, OTEC, exploits a gradient that the ocean maintains free of charge at all hours in all weather wherever warm tropical surface water sits above the cold depths. Surface water in equatorial regions sits at 25 to 28 degrees Celsius. Water below 1,000 meters sits at 4 to 6 degrees Celsius, year-round, regardless of what the weather is doing above. That 20-degree differential is sufficient to run a continuous heat engine. Warm surface water evaporates a working fluid with a low boiling point. Ammonia is the standard choice. The expanding gas drives a turbine and generates electricity. Cold, deep water drawn from 1,000 meters condenses the gas back to liquid, closing the cycle. The plant runs continuously, forever. Thermal efficiency is low, 3 to 5% compared to a natural gas turbine's 40%, but the fuel is free and inexhaustible, and the plant operates at night, in cloud cover, in flat calm, in any conditions short of the structural limits of the platform itself. OTEC is baseload power for tropical ocean environments. Japan's Kumejima facility, the most mature grid-connected OTEC demonstration currently operating, has proved the concept works at demonstration scale. The cold water pipe, descending to 1,000 meters with a diameter around 10 meters for commercial scale, remains the central engineering challenge. It must be simultaneously light, storm-tolerant, corrosion-resistant, and hydraulically efficient. But it has been built. The physics is proven. And OTEC has two co-products that transform its value proposition entirely. When cold, deep water is pumped to the surface for the condensation cycle, it carries dissolved nutrients from the deep, the same upwelling chemistry that drives productive fisheries in cold current zones like Peru, Norway, and Newfoundland. That nutrient-rich cold water can run through the Blue Commons aquaculture systems before discharge, feeding the shellfish and seaweed farms with the same biochemical richness that makes wild cold ocean fisheries so productive. And the temperature differential between the cold water and the warm surface creates conditions useful for low-energy desalination as a secondary co-product. OTEC's cold pipe is not a cooling loop. It is an energy, water, food system in a single installation. The Blue Commons community of 100,000 generates a smaller waste stream per capita than almost any equivalent land city on Earth, not from ideology, but from engineering necessity. When you cannot flush things away, you design closed loops from the beginning. Food waste and biosolids go through anaerobic digestion, generating methane for supplementary heating and digestate for fertilizer. Constructed wetlands and reed bed greywater systems, sized at roughly 0.8 square meters per person, polish wastewater while doubling as biophilic public green space. The resource loop is not perfect and never will be. Membrane replacements, metals, medical waste, and specialized chemistry all still require external supply chains. But the Blue Commons is radically leaner than any land city built without designing for closure from the outset. Before the Blue Commons could become what it became, however, it had to solve one problem that no amount of engineering could dissolve: governance. In 2017, the Seasteading Institute announced an agreement with the government of French Polynesia to establish the world's first semi-autonomous floating zone in the South Pacific, a community exempt from French Polynesian law, free to experiment with alternative governance. The announcement attracted significant investment. By 2018, the agreement was dead. The governance structure its founders imagined, freedom from existing law as the central selling point, was precisely the feature that made it politically impossible to build. The pattern is consistent. Under the United Nations Convention on the Law of the Sea, a floating structure in a country's exclusive economic zone is subject to that country's jurisdiction. A floating city cannot become sovereign simply by floating. Ocean cities do not eliminate law, they multiply it. Maritime law, municipal law, environmental law, property law, insurance, emergency doctrine, and building code, all converging simultaneously on a structure that no existing legal framework was designed to accommodate. The Blue Commons succeeded by building new institutional infrastructure within existing frameworks. Busan extended its municipal jurisdiction outward over the platform district. The Maldives framed the Ring Atoll as climate adaptation infrastructure under national law and international treaty. These are not compromises. They are the engineering of governance, as necessary and as deliberate as the engineering of the hull. The ground does not have to be permanent, the law does. And the Blue Commons has one final advantage over every land city ever built: it can move. A full relocation takes months of engineering planning, but in the 2050s, two mature floating cities relocated from high-risk cyclone zones to sheltered deep-water moorings as storm intensity increased. Impossible for any land-based city, a demonstration that permanently retired the ancient equation of permanence with civilization. The Blue Commons can house 100,000 people, feed 30% of them locally, power itself on the ocean's own thermodynamics, and move when the ocean turns hostile. It is the most advanced city ever built at its scale, and it is entirely on the surface. Below it, a different world is becoming possible. There is a moment in the development of every mature floating city when its designers look at the space directly below their feet, the water immediately beneath the platform, protected from wind, weather, stable in temperature, biologically extraordinary, and make the obvious choice, the choice to go down. The first generation of floating cities was flat, a platform at the waterline, buildings on top. But as the Reef District and Blue Commons matured, the space immediately below the waterline revealed itself as premium real estate, protected from wind and weather, stable in temperature year-round, vibrationally isolated from the activity above, surrounded by biological life that had colonized the hull with increasing density every year. Second-generation cities added a submerged lower deck, 1 to 3 meters below the surface, housing mechanical systems, aquaculture chambers, cold storage, and workshops. Third-generation cities, the shelf city model, went further, a transparent gallery tier at 5 to 8 meters depth, where residents could sit in pressurized viewing rooms surrounded on all sides by the biological life that had colonized the city's hull, not looking through a window at the ocean, surrounded by it on 3 sides simultaneously. Sitting in the gallery tier of a mature shelf city, looking out through 3-centimeter acrylic at a hull now 20 years old, its surfaces completely invisible under coral, sponge, Gorgonian fan coral, and encrusting organisms, its mooring arches turned cathedral by 2 decades of marine colonization, you understand something about cities that land has never been able to teach. Cities are not structures, they are ecologies. But ecology in a sealed environment has a dark side, and the most important lesson in closed habitat design came not from the ocean, but from a glass building in the Arizona desert. In September 1991, 8 researchers sealed themselves inside Biosphere 2, a $200 million glass-enclosed facility designed to be a fully self-sustaining ecological system. The concept was rigorous. The participants were scientists, engineers, farmers, and ecologists, selected and trained with care. The intention was serious. Within 4 months, something was wrong. Oxygen levels were dropping, not by a fraction of a percent, measurably, continuously, persistently dropping. The standard atmospheric oxygen fraction, 20.9%, fell month after month. By the experiment's 475th day, it had reached 14.4%, the equivalent of the air at the summit of a high Andean peak. The 8 biospherians were experiencing altitude sickness inside a sealed facility in a desert. The cause was not the humans breathing too much. The investigation found 2 unexpected sinks. First, intense microbial respiration from the organic-rich soils, consuming oxygen at rates the models had not predicted. Second, and more surprising, the concrete walls. The facility's concrete was still chemically curing. In a process called carbonation, fresh concrete combines with atmospheric CO2 and, in doing so, also captures oxygen from the atmosphere through secondary reactions. The designers had modeled concrete carbonation using standard parameters. Those parameters were not accurate for a fully sealed system over years of continuous occupation. The concrete walls were, in a slow and invisible way, eating the atmosphere. The lesson is the most important in sealed habitat design. The closed ecological systems fail from the sinks you didn't model, not the ones you did. This lesson was applied with full rigor in the design of the shelf cities below deck tiers. Air revitalization is not treated as background infrastructure. It is treated as cognitive load-bearing structure. A 2023 meta-analysis found CO2 concentrations between 1,000 and 5,000 parts per million, achievable in poorly managed enclosed spaces, measurably impair cognitive performance on complex tasks, with increasing effect as levels rise. In the submerged tiers of the shelf city, CO2 management is monitored with the same precision as structural integrity. Beyond chemistry, there is psychology. The ESA's Mars 500 program, a 520-day sealed isolation simulation in Moscow, found progressive reduction in physical activity, measurable decline in lower limb neuromuscular performance, disrupted circadian rhythms, and accumulating psychological stress even in carefully selected, professionally trained crews. And long-duration sealed living research consistently identifies one category of loss that no engineering specification explicitly accounts for: micro-restorative experience. The small, usually unnoticed sensory events the natural world provides continuously: weather, breeze, distance vision across open terrain, the difference between morning light and afternoon light, the sound of something unpredictable. When those things are absent, attention fatigues, interpersonal friction accumulates, well-being erodes, not with visible drama, but persistently. The shelf city's architectural response is the spectral city, a living environment designed to substitute deliberately for what the natural world provides accidentally. Spectral light programming that cycles through the full solar day, including ultraviolet wavelengths important for vitamin D and circadian entrainment. Acoustic environments with biological complexity and spatial variation rather than engineered silence. Green spaces built not for food production but for psychological function. Plants chosen for their restorative effect rather than their caloric yield. Temperature variation systems that create a mild diurnal thermal gradient, telling the body that time is passing. The transparent gallery tier itself, which gives residents a distance vision environment and a biologically rich visual field that no sealed room above the waterline can replicate. By the 2050s, the major floating urban districts had been occupied long enough for children to come of age who had never had another address. Those children, the first truly ocean-native generation, experienced the shelf city not as an adaptation to challenging circumstances, but as the natural condition of human life. They found land strange, its stillness, its solidity, its complete insulation from the ocean's presence. They were the first humans since the great maritime cultures of the Pacific for whom the ocean was not a destination, it was home. And they were looking downward with curiosity. The shelf city mastered the space just below the waterline, but the ocean doesn't stop 5 meters down. It goes down kilometers, and the descent to the next level requires a completely different kind of engineering and a completely different kind of person. The descent from the surface to the first permanent underwater habitations was not driven by ideology or ambition. It was driven by maintenance. The mooring systems, bioreceptive hulls, cold water pipes, and subsea infrastructure that keep the Reef District and Shelf City alive are all below the waterline. Managing them from the surface, sending divers down repeatedly for short working periods, is expensive, dangerous, and insufficient for the precision that decades-long infrastructure management requires. The solution already existed in the offshore oil industry: saturation diving. Workers live in a pressurized habitat at depth, equalized to the ambient water pressure, allowing them to work in the surrounding ocean for up to 8 hours per day without the repeated decompression penalty that surface-to-depth diving would otherwise impose. A saturation worker at 35 meters can rotate 2 weeks at depth before a single, slow, carefully managed ascent. The habitat is simply their home for the duration. What the saturation maintenance teams discovered within a few years of regular rotations was that the underwater environment, once you were physiologically adapted to it, was not hostile. It was extraordinary. At 30 to 40 meters depth, natural light from the surface still reaches you. Not daylight as it exists above water, but a deep cobalt glow that shifts constantly with the wave action above, patterning the hull surfaces with moving ripples of refracted light. The life at this depth is dense and active. The hull structures, covered with coral and invertebrates after even a few years of immersion, move with permanent biological activity. The sound at this depth is unlike anything audible at the surface. The low, resonant hum of water moving past structure, the creak of the mooring cables, the intermittent percussion of crustaceans in the reef, the occasional low thrum of a large animal passing at the edge of visibility. Through the observation concourse, a curved section of the habitat where the outer wall is entirely 3-centimeter acrylic, providing a 180-degree view of the surrounding reef, the environment is one of the most beautiful ever to have surrounded a human being at work. NASA understood the value of this environment early. The NEMO program, NASA Extreme Environment Operations, has used Aquarius Reef Base, located 19 meters below the surface off Key Largo, Florida, since the 1990s to simulate the operational conditions of space exploration. Astronauts, engineers, and scientists live in Aquarius for up to 3 weeks, conducting simulated extravehicular activities, testing telemedicine, practicing delayed communications protocols. Aquarius is a space analog not because it resembles space physically, but because it imposes the same operational isolation. You cannot easily leave, resupply is limited, medical transfer is slow, and system failures have no grace period. The Poseidon Station model extended the saturation habitat into permanent residential occupancy, not workers on rotation, but residents. The physics of living underwater at saturation pressure means residents can step directly from the station's egress locks into the surrounding ocean. No diving apparatus needed beyond basic breathing equipment, because their body is already equalized to the ambient pressure. They can sit in the observation concourse and watch the reef surface, the underside of the shelf city above them, as it moves in the slow currents of the platform's thermal shadow. Entering Poseidon Station for the first time is disorienting in a specific way that has become part of the experience. You descend in the elevator, and the light changes. The neutral white of the access tube gives way to the cobalt blue filter of real ocean light entering through the station's observation surfaces. The ambient sound drops from the mechanical hum of the platform above to something older, water moving against structure, the biological choir of the reef. The visual field opens as you enter the observation concourse, the ocean present in every direction, the shelf city's colonized hull above you, a cathedral of living architecture, 30 years of marine accumulation growing from every surface. The pressure question is not whether this environment is habitable, it is whether it can be maintained safely for decades at increasing depth. And this is where the physics of the descent imposes its categorical change. Pressure rises by 1 atmosphere for every 10 meters of seawater. Poseidon Station at 35 meters experiences approximately 4.5 atmospheres of absolute pressure. At 100 meters, that figure is 11 atmospheres. At 200 meters, 21. At 500 meters, the depth of the next city, 51 atmospheres press inward on every square centimeter of the structure continuously. Not during a test, not at maximum rated load, continuously for a century of occupied operation. Withstanding pressure once and remaining habitable for 100 years are in underwater engineering entirely different thresholds. The gap between them is where most conceptual underwater structures have historically failed, and where the designers of the next habitat spent the longest time. Poseidon Station proved you can live at 35 meters depth and thrive there. The Blue Garden is a city at 500 meters. The physics are different in the way a handshake is different from a structural weld, and the view from inside is unlike anything else that has ever existed. At 500 meters depth, the ocean is not dark. It is not bright either. No sunlight reaches this depth in usable quantities. But the ocean at 500 meters is filled with a faint, continuous biological luminescence, the cold blue flicker of bioluminescent jellyfish and copepods, the slow metabolic glow of organisms that have never required the sun. If you were suspended in open ocean at 500 meters with no light source of your own, you would see, barely unmistakably, a living light show, microscopic and perpetual. The abyss is not empty. It glows from within. This is the view from inside the Blue Garden. The Blue Garden is Shimizu Corporation's engineering specification for what is, by any measure, the most complex single structure ever designed for permanent human habitation. The outer walls are large triangular acrylic panels, each one the size of a tennis court, held in a geodesic lattice of fiber-reinforced polymer ribs. At 500 meters, the ocean presses inward on every square centimeter of the sphere's exterior with 51 atmospheres of force. The engineering of each panel, each joint, each dynamic seal accounts for that force not for a test condition, continuously for 100 years of occupied operation under cyclical thermal variation and the slow creep that all materials exhibit under sustained compressive load. That distinction, withstanding pressure once versus remaining habitable for a century under sustained load, is the entire design problem. It is why the Blue Garden specifies acrylic panels rather than glass. Acrylic creeps predictably under sustained compression, and that predictable creep can be designed for. It is why the geodesic FRP frame rather than a conventional structural system. Geodesic geometry distributes compressive loads uniformly across every element, eliminating the stress concentrations that flat panels and right-angle frames create. Every design decision in the Blue Garden is a response to the difference between a threshold load and a lifetime load. Inside, 5,000 residents live at standard atmospheric pressure. What they experience is something no land city, no surface floating city, and no shallow underwater habitat can offer: the deep ocean, visible in every direction, from every window, at all times. The interior organizes as 15 curved residential floors, each bending to follow the sphere's geometry, each one's outer wall forming a section of the acrylic shell. From the upper floors, the faint blue glow of sunlight filtered through 500 meters of seawater reaches residents, more felt than seen, like light through very thick frosted glass, a reminder that the surface exists. In the lower floors, there is only the bioluminescent dark and the shapes of deep ocean life drifting past the glass. Fish, jellyfish, the slow particulate fall of organic material descending from the sunlit world above, circulating endlessly through the deep water column. The residents of the Blue Garden's lower floors live in the most visually extraordinary permanent human environment ever constructed, surrounded on all sides by the living dark of the deep ocean. The city runs on the cold. At 500 meters, the deep OTEC cycle works differently from its surface equivalent. Water drawn from 1,000 meters is measurably colder than the ambient 500-meter environment, and that differential drives a continuous baseload generation cycle for the sphere's 5,000 residents. The same cold water carrying dissolved nutrients accumulated over centuries of slow settling from the surface passes through hydroponic cultivation chambers before discharge. At 500 meters, those nutrients are more concentrated than anything surface agriculture can access without industrial chemical inputs. The Blue Garden's food chain runs not from sunlight, but from the geochemical wealth of the deep water column. Microalgae culture at this depth achieves protein densities of up to 70% of dry biomass in optimized strains, a protein concentration no plant crop can match. But the most extraordinary feature of the Blue Garden is not the sphere, it is the descent. The infraspiral is a sealed infrastructure tube approximately 15 kilometers long, roughly the length of Manhattan, descending from the base of the Blue Garden at 500 meters to the seabed industrial node at 3,000 to 4,000 meters depth. It is helical, a continuous slow descent, each revolution adding roughly 200 meters of depth, every meter of it pressurized, lit, and accessible. O-Tech cold water pipes run through the core. Emergency escape capsules wait at stations every 500 meters of descent. Maintenance teams travel its length in pressurized transit vehicles, watching through reinforced acrylic viewports as the depth counter climbs past numbers that have no equivalent in any other occupied structure on Earth. At the base of the spiral, the Earth Factory, the seabed is ancient and undisturbed. No daylight has reached it in geological time. Geothermal energy is drawn from the crust through circulation wells. CO2 captured from the sphere's atmosphere is sequestered into deep geological formations. Mineral deposits are processed from deep water sediments. The materials the Earth Factory produces travel up the infraspiral to the platform economy above, a supply chain running vertically through the water column, connecting the geological past to the inhabited present. Descending the infraspiral from the Blue Garden to the Earth Factory is one of the most remarkable journeys available to a human being who has not left the planet. The first kilometers are familiar. You are in a city, surrounded by the ordinary texture of urban life. The first kilometer of descent is lit amber, warm tones specified for psychological grounding as depth increases. At 2 kilometers, the viewport shows geological seafloor that no human eye ever saw before this structure was built. At 3 kilometers, the pressure outside is 300 atmospheres. Through the reinforced viewport, the ancient, undisturbed seabed is 3 meters away. For the residents of the Blue Garden, the primary psychological adaptation challenge is not claustrophobia. The sphere is vast, its visual field open. It is micro-restorative deprivation, the absence of the small sensory variations that the natural world provides at the surface without effort. The Blue Garden addresses this with the full spectral city protocol, programmable dawn-to-dusk light cycling across the complete solar spectrum, biophilic green spaces designed for psychological function, acoustic environments with biological complexity and spatial variation, and the scheduled deep shift when the sphere's interior lights dim and the external ocean illumination is adjusted, and the entire city experiences simultaneously the living dark through its walls. The ocean-space mirror is visible here with great clarity. Space habitats resist outward pressure from internal atmosphere against vacuum. The Blue Garden resists inward pressure from the ocean against its internal atmosphere. Opposite forces, identical life support architecture. Closed-loop water recovery, sealed atmosphere management, CO2 scrubbing, circadian design, psychological engineering for confinement, maintenance culture where no system can degrade undetected. NASA has been explicit about this. NEMO uses Aquarius as a space analog, precisely because the operational constraints are structurally identical. The ISS now achieves approximately 98% water recovery after its 2023 brine processing milestone, almost exactly the closure rate the Blue Garden would eventually need for fully autonomous operation. The ocean is not merely an engineering challenge, it is the proving ground for the capabilities that will one day take humanity beyond it. 3 Blue Garden cities now exist in the equatorial Pacific. The residents call the ocean floor outside their windows the Commons, not as a legal category, as a cultural one. The deep ocean that surrounds them is understood as the shared ground of a civilization that lives within the sea rather than upon it. They are the first people in history for whom the sun is optional, and they are not the deepest. 3 Blue Garden cities, 15,000 people at 500 meters, the most technically sophisticated human habitat ever built, and in the long timeline of ocean civilization, still understood by those who built it as a proof of concept for something much larger. Everything described in this episode has been real engineering, costed technology, and inhabited habitat. What comes next is in the master planning documents of engineers and architects alive today. It is not yet funded, not yet built, but it has a name and a location and a scale that makes the Blue Garden, for all its ambition, for all its 51 atmospheres and 15-kilometer descent, look like a pilot study for something much larger, much stranger, and in a way that resists easy description, much more human. At 800 to 1,000 meters below the surface, the continental shelf creates a broad, relatively level plateau extending for hundreds of kilometers off the edges of the great land masses. At the right depth for deep OTEC, directly above the geothermal gradients of mid-ocean ridge systems, adjacent to the most nutrient-rich upwelling zones in the ocean, this topography is what the designers of New Atlantis identified as the ground floor. Not a vertical Blue Garden with a descending spiral, a horizontal city spreading across the continental plateau the way land cities spread across plains. Multiple large pressurized spheres linked not by tubes descending through the water column, but by deep pressure transit tunnels running across the seafloor. Spaces large enough that the ceiling, the underside of the ocean, 800 meters above, is so distant it cannot be seen. Districts, neighborhoods, open civic plazas sealed against a pressure that makes the word outside meaningless in any sense a surface human would recognize. Not a habitat looking at the deep, a civilization looking at itself with the deep on every side, built from within it. The people who will live in New Atlantis have not yet been born. The people who are designing it are alive today. And there is one thing about New Atlantis that separates it finally and completely from every ocean city that came before it. One feature that makes the Blue Garden look like a beginning. That feature requires its own story, its own hour, its own episode. That episode is coming to this channel. But before it does, this is what New Atlantis looks like from outside. You are in a submersible, descending. The surface left you 40 minutes ago. Since then, the blue has deepened through cobalt to navy to the absolute lightless black of the open ocean at depth. A darkness with weight and presence to it. A darkness that feels less like an absence than like a substance. The external lights show you 3 meters of ancient seafloor in every direction. Undisturbed sediment. Geological time recorded in particles that fell from the sunlit world above for 1 billion years and settled here in silence. Then the pilot says, "There!" You look up from the viewport. You look outward, not above you, below you. You crest a shelf edge, and there, spreading from horizon to horizon across the ocean floor, is light. Not scattered and faint, not the cold flicker of organisms in open water. Light. Cities. Towers of amber and blue rising from the shelf surface, corridors of illumination connecting sphere to sphere across the plateau, the slow movement of transit vehicles between structures, the inhabited, unmistakable civilizational glow of human beings who decided that the darkness was not a reason to stay away. It is the most beautiful thing you have ever seen. It is upside down. The stars are gone. The cities are here.